Welcome back to Physics 371 Online. We're going to finish up this section of the textbook by briefly reviewing capacitors and capacitance. And very simply, a capacitor is just an arrangement of conductors that's used to store electric charge. And the way we do this is by taking your arrangement of conductors shown here in the diagram as two parallel plates, which are conductors, and connecting them to a power supply, like a battery. So charge is able to flow from the battery, and equal and opposite charges will be deposited on the two plates of the capacitor when equilibrium is reached. The ability of this capacitor to store charge is quantified by what we call the capacitance. And the very simple definition is the magnitude of the charge stored on each plate divided by the potential difference that was used to store it. The unit of capacitance in the SI system, coulombs per volt, can be expressed in more fundamental units, but we give the name the farad to express the coulomb per volt. Now, how do we calculate capacitance? Well, the specific value that we get for a particular arrangement of conductors depends on the size and then the geometry, the arrangement of the conductors that are being used. We can't always calculate exact expressions for the capacitor, but we can usually get good approximations by using Gauss's law and the definition of electric potential difference. So here are the steps, several of which just belong to the process of using Gauss's law to find an electric field. So we first, given a particular capacitor arrangement, assume that we connect it to a battery and that the capacitor plates get charged up to plus and minus Q as their charge. Then, using the symmetry of the arrangement, we sketch the electric field lines and use Gauss's law to find an expression for the electric field. After that, by choosing a simple path between the two conductors, we can find the potential difference between them using the definition of the electric potential difference. And finally, then we go back using the definition of capacitance, write that as Q over the expression that we've obtained for delta V, take the absolute value because the capacitance is always a positive quantity, and that will give us an expression. And you might wonder, well, what's going to happen to this Q? Because we just assumed a particular Q in starting. Well, the denominator of the electric potential difference will always contain Q in it. So in all of the calculations that we can do easily, that Q will drop out. And in fact, that's very significant because the capacitance of a particular arrangement of capacitors should not depend on the amount of charge. What the definition of the capacitance shows here is that if we were to, for example, double the potential difference, we would simply double the charge because the capacitance does not depend on the potential difference. Let's do an example. A very familiar case that you probably have seen before, so this will simply refresh your memory of how to find the approximate capacitance for a parallel plate capacitor. Assuming two parallel plates that have area A and separation D, what will be the capacitance? So we first of all, following the first step, assume that the plates are charged with equal and opposite charges Q and draw the electric field lines. And by symmetry, as long as we stay far away from the ends of this parallel plate arrangement, the electric field lines will simply point horizontally from the positive to the negative plate. And we assume a cross-sectional area A for each plate and a separation distance D. Now, we draw the field lines from a side view, and we'll see exactly how this looks, and the choice of which Gaussian surface to use to apply Gauss's law comes next. And this could be a cylinder, but I'm going to do the calculation for a Gaussian cube. Remember, it's a closed surface, and so even though this may look like a square, it really represents a cube with a face area that we'll call A0. And it's very important, the location of the cube. We put one face of it inside the conducting object on the left and the other one in the region where we're trying to find the electric field. So the expression for Gauss's law involves calculating the integral of E dot dA on every part of the closed surface, and that's simply the electric flux. So we can see that on the left-hand face, where I'm showing on the cursor, the flux is 0 because the electric field is 0 inside the conductor. So that makes it easy. What about the right-hand face? Well, the right-hand face is also easy because the electric field is horizontal and the dA vector would also be horizontal. So the integral of E dot dA just gives E times the area. So it would be E times A0. Again, because the electric field vector and the dA vector are parallel. Finally, on the four other faces, we can see that the dA vectors will point perpendicular to the electric field on all four of those. Therefore, they will contribute nothing to the flux integral. So, using Gauss's law, we've talked through the evaluation of the left-hand side, which for a cube has 6 pieces. So 5 of those give 0, leaving on the right-hand face E times A0. Q enclosed, the Q that's actually enclosed by this cube, will be related to the amount of area of the face of the cube. And it will be the surface charge density on that plate multiplied by the area. So if there's a total charge Q and an area A for the conductor, Q over A is the surface charge density, charge per unit area. And then we multiply by the smaller face area of the Gaussian cube to give us Q over A times A0. We see that the A0 terms drop out, and we find that E is Q over A times epsilon 0. The next step then is to use this expression to find the electric potential difference between the two plates. So the key here is that the electric potential difference should not depend on which path we choose. So then it would behoove us to choose the simplest path possible, the path that would make the integration as easy as it can be. So if the electric field is horizontal, it would make sense for us to do an integration along a path that's parallel to the electric field, like this. So integrating from the left plate to the right plate, our dl vector points in the direction of E. And then that makes the evaluation of the potential difference integral much simpler. E dot dl is just E times dl if those two vectors are parallel. And the E, as long as we're far away from the edges of the plate, so we're going to be approximating a very, very large parallel plate capacitor. We can take the E outside the integral because on the previous slide we saw that the electric field did not depend on distance. It was uniform in between the plates. So the E comes outside, and what's left is the trivial integral from the left plate to the right plate of dl, and that's simply the plate separation d. So substituting for E, that gives Q over A epsilon 0. The integral that's left gives d, and so we have an expression for this potential difference. So we're ready to finish it off. The only thing we have to do is plug back into the expression that defines the capacitance as Q over delta V. So the numerator is Q, the denominator is QD over A epsilon 0. When we take the absolute value, the sign goes away. So the Q drops out just as I said it would, and we get epsilon naught A over D, a result that depends only on the size through A, and then the shape or the arrangement of the conductors, and that has to do with the spacing D. So this is a familiar result for an empty parallel plate capacitor. Something similar can be done, and an example in the book is done for the 2D case of a cylindrical geometry, and then you can have a 3D spherical case as well. So once again, remember that Gauss's law can only be used in certain very high symmetry situations, and these are the only cases that we can actually use to calculate the approximate capacitance. Finally, we end this section by talking about a straightforward calculation for how much energy can be stored by a capacitor, because that's really what a capacitor is useful for. If you connect this arrangement of conductors up to a battery and wait a second for it to charge up, you then can disconnect the battery, and now you've got charge that's stored on the two conductors that can be used for lots of different purposes. And we talked about in class how you can make a defibrillator, you can make a spot welder, you can make a flash for a camera by connecting a capacitor to a suitable load. So what kind of energy expression do we get if we want to quantify how much is stored by a particular capacitor? So here what I want to do is imagine that we've connected a capacitor to a battery with a certain potential difference, V final, and then we close the switch. And imagine the process, it does take a finite amount of time, but imagine the process partway through. So the potential difference has not reached the final value, but it's not zero anymore either. So this instant of time, at that point the potential difference across the plates will be V, and the charge on the plates will be plus or minus Q. So at that point, it'll require an amount of energy of du equal to V dq to move a tiny amount of charge, dq, through that potential difference. So we can get the total energy that's stored by adding up the work that's done, this energy, starting from an initial charge of q to the final charge, capital Q. All right, so here's the picture. At some point, we've got a partial amount of charge, plus and minus little q. If the capacitor has a capacitance C, then the potential difference between the two is just Q over C from the definition of capacitance. And we're now imagining moving a tiny amount of charge dq, if it's positive, moving it from the negative plate to the positive plate. So the expression for the energy that's required is the du, that's V dq. That's how much is needed to move the tiny element of charge dq. And then we simply integrate that quantity from Q equals 0 to the final charge, which is the maximum charge that can be stored, and we'll use capital Q for that symbol. So this is easy. We have an expression for the potential difference between the plates as Q over C. So we make that substitution, and now we can straightforwardly integrate the charge. Q over C dq will give us a Q squared over 2, and then we substitute in the upper limit, which results in half Q squared over C. That's the energy that's stored in this capacitor when it's been fully charged. And if we substitute in Q equals CV, which again comes from the expression for the capacitance, we can write this in a slightly different form as U equals 1/2 CV squared. Strictly speaking, using my original formulation of the problem, the potential difference V final is the potential difference of the battery, so that should be in this equation down here, but at this point, notation, it's a little more convenient if we just let V equal the potential difference of the battery. So 1/2 CV squared. Both of these two expressions are equivalent to one another, and which one you use just depends on what kind of quantities that you're given if you want to calculate the energy stored. So here you can see that for a given capacitor, if you double the potential difference, you raise the stored energy by a factor of 4, and that's relatively significant. All right, hope this overview is helpful, and we'll probably work on some more examples in class.